and galaxies formed in the first billion years or so after the Big Bang, and how we can study that epoch of our universe. So what I'm talking today can be broadly considered as research that addresses one of the fundamental research areas and problems of modern physics, the so-called cosmic origin problem. Where are we coming from? How did the first generation of stars and galaxies transform the universe, which initially was very simple, very homogeneous, to the complex universe with stars, galaxies, black holes, planets, and life on those planets, and here on Earth trying to figure it all out. So how did that process start, and how it continued throughout the 14 billion years or so since the Big Bang. And today I'm going to focus primarily on a very short epoch of time. I'll talk about what is happening in the first billion years or so after the Big Bang, and more specifically from about 300 million years after the Big Bang, when the first generations of galaxies started to form, to about 1 billion years after the Big Bang, when we already had quite a number of galaxies in place, some brighter than our own galaxy, the Milky Way. So the galaxies we'll see had the opportunity to form quite efficiently, quite rapidly already early on, and to contribute to grow complexity of the universe. Stars and galaxies transforming the light elements into the heavier elements, and then preparing the interstellar gas for subsequent generations of star formations. And within this broad theme, in particular, one open question that astronomers such as myself are trying to understand at the moment is, well, how was star formation back in those first early moments in the history of the universe? With the Hubble Space Telescope, we'll see we can spot some galaxies which are quite far away from us, and we'll see, because of the finite speed of light, we observe those galaxies as they were when the universe was young. So if we take a galaxy such as the one shown on the right here, 13.4 billion years ago, this is the most distant galaxy that we know of. It's called GNZ11. GN stands for Goods North, the field observed with the Hubble Space Telescope in which we have found the galaxy, and Z11 stands for the redshift 11. And we'll see again what that means. Means about 400 million years after the Big Bang, or 13.4 billion years ago. So this galaxy, very fuzzy, we collect only a few photons, even with our most powerful telescope, the Hubble Space Telescope. Is forming stars at a rate similar to galaxies that we can find in the local universe, and that we can observe in incredible amount of detail, as we can see on the left side. And so, was star formation in those early systems, such as GNZ11, equal or different from the star formation processes that we can observe today? And if we think about the physics back then compared to the physics today, we can realize that we had different physical conditions. The chemical composition of the gas out of which stars were formed was different. In general, there were more light elements and less of the heavier elements, or for astronomers, metals, because we have a very simple periodic table. We have hydrogen, helium generally, and then we tend to refer in astronomy to all other elements, those produced inside stars and from exploding supernovae or merging neutron stars, as metals. So gas had a different chemical composition. There was less radiation around from other stars. However, the cosmic microwave background radiation, in contrast, was higher. So the gas could not cool down to the 10 Kelvin or so that we observe in the molecular clouds that then are going to be stellar nurseries in the local universe today. So it was quite different. And so it's not unexpected to have different star formation properties. And that's the question that astronomers such as myself are trying to figure out. And how are we going to do so? Well, we can take advantage of the fact that light takes time to reach us. So if we use our most powerful telescopes to observe the most distant galaxies, we are collecting light, we are collecting information about how galaxies were back in the infancy, in the youth of the universe. And with the Hubble Space Telescope, we can reach an epoch we'll see out to 400 million years after the Big Bang. So not quite the very first generation of stars and galaxies formed, based on comparison to theoretical and numerical models, but we get pretty close. So maybe we see second, third generation galaxies with Hubble. And if you're not familiar with this idea that the most distant objects are observed when the universe was young, we can spend a moment with an analogy about how information is transported on Earth. And so think about Bob writing a letter, an old-fashioned letter to his friend Alice. So Bob writes now about something which happened just at the time that he writes the letter. Then he posts the letter. The letter will be delivered maybe in a few days later, and Alice opens up the letter and gets information about how Bob was back in the past. So information has taken time to travel from Bob to Alice. That's the same thing that happens for photons. Photons, light transport information, very much like a letter in the mail. It takes time for information to reach us because the speed of light is finite. So when we receive information, the photons from the distant galaxies, we get a snapshot of how they were in the past. In addition, the universe started expanding with the Big Bang and has continued expanding. So the distant galaxies move away from us as the universe expands. That's called the Hubble law. Then because the universe is expanding, the photon wavelength, as the photons travel from those distant galaxies to us, gets redshifted. The photons get stretched to longer wavelengths. So we get a red shifting of the light. So what happens is that if we have a young blue galaxy forming stars and very far from us, the photons start out blue, and by the time they reach us, they become red. And then we observe them with the Hubble Space Telescope, for example. So the more distant a galaxy, then, the redder we expect the light to be. Now, that creates both an opportunity because we can just take images rather than spectra and try to identify those galaxies that might be quite far from us, but also creates a bit of a problem because Earth's atmosphere absorbs light, in particular at infrared wavelengths, and also blurs the images. So we gain an advantage by placing our telescopes up in space above Earth's atmosphere. So we can get no absorption or emission of light from the atmosphere itself, which would create a background which prevents us to see the faint objects, and there is no blurring of the images. So if we compare the same image of a small region of the sky taken from the ground or from space, we really see the difference. So this is a part of the field Goods North, the field in which we found that very distant galaxy at redshift 11. So the light of that galaxy had been stretched 11 times in wavelength. And here we are looking at another patch of the same field. We're just looking at a group of galaxies that are interacting a little bit with each other. We are looking at it on the left of this image with the Subaru Space Telescope. It's an 8-meter telescope located on Mauna Kea in Hawaii. It's one of our best telescopes on the ground. You can see, in contrast, the image of the same field taken with the Hubble Space Telescope. The Hubble Space Telescope is in orbit above the atmosphere, about 600 kilometers above the surface of Earth. It is a smaller telescope, only 2.4 meters in diameter. So it collects a fewer number of photons and in principle would be affected by more diffraction. But despite that, we can see that the Hubble images are sharper, they have greater angular resolution, and they can also identify fainter sources, so they have less background, higher signal to noise. So that gives you an idea why, to observe the young universe, space telescopes such as the Hubble Space Telescope are very, very useful. So if we put all these together, what we want to do if we want to study the most distant galaxies, those early in the universe, is that we need to find in the sky sources that are red, and because they are very far away, they are also quite faint. They are also pretty rare because at the beginning, only a small numbers of galaxies were being formed per unit time and per unit volume in the universe compared to galaxy formation at later times. So we need a large investment of telescopes time to search in the infrared in multiple bands at multiple wavelengths, and then we can do an approximate color selection to find those red galaxies that we think are good candidates for being very distant, and then we can refine the samples further with more sophisticated data analysis. This is an image with about 5 hours of exposure with the Hubble Space Telescope. We can find a few thousand galaxies, mostly black sky. Here there are a handful. It's an image that I took back in 2010, and it's particular because it has an overdensity. It has 5 candidate galaxies quite far away, all clustered together and relatively bright as our own galaxy. Let me see. So I have a couple of questions, and I think I'll try to answer them as we go make sure that everyone is following. What is the limitation of wavelength by space telescopes? Well, we have space telescopes that are observing at all wavelengths. For the Hubble Space Telescope, Hubble is capable of observing from the ultraviolet to the near infrared. So from about 0.3 micron to 1.7 micron. And indeed, it's very expensive to put telescopes in space. That's why we generally put smaller telescopes in space to make sure that we can observe at those wavelengths, for example, in the X-rays or in the further infrared, where we cannot do it from the ground, or we do something such as Hubble to get really sharp deep images in the optical and near infrared. And then we use larger telescopes on the ground to collect more photons, for example, to do spectroscopy rather than imaging. Indeed, long wavelength, the radio observations are some of those that you do best from the ground because the atmosphere is very transparent to radio waves. Minimum and maximum frequencies, well, we go really from the ultra long radio waves, so meters waves. We go down all to the infinite, very small with hard, for example, gamma rays. But let's now go back to the visible near infrared. And here is an image with 5 hours of exposure with Hubble. Let's see what happens if we instead stare at a small patch of the sky for a longer time. Same also with the Hubble Space Telescope. This is an image called the Extreme Deep Field that has been obtained by 23 days of exposure time with Hubble. And now you see it's the same size image. There is less empty space. There are more galaxies appearing here. So these images can be used to study galaxy formation and evolution across cosmic time. So we can take images such as the Hubble Extreme Deep Field and ask ourselves, how many galaxies do we find in the universe? How far they are? How old? Are the properties of galaxies evolving with time or not? Just to give you a simple flavor of calculations and science that we can do with an image like this one, let's ask ourselves briefly, how many galaxies are there in the universe? So this image, if we were to count all the galaxies, we would find a little bit more than 5,000 galaxies. Then we know that's a tiny part of the sky. We would have to do a tiling, repeating the observations about 30 million times to cover the full sky. So we can assume that the number of galaxies in the universe would be 5,500 times 13 million. We get about 70 billion galaxies in the universe that we can observe with Hubble. And since that's one of the deepest images, that's like our best estimate of the lower number of galaxies that we have in the universe. And we think that that's a pretty good number. Maybe there are 100 billion galaxies in the universe. It's a round number that I like to use when I explain how many galaxies we have in the universe. So very simple way of deriving that number just from this image. If we do a bit more science with the image, we can use images such as the Hubble Extreme Deep Field to characterize the so-called galaxy luminosity function. So the galaxy luminosity functions from a research paper that we published with Richard Bowens, a professor at Leiden University a few years ago, is shown here in this plot, where we have on the vertical axis, the log of the number of galaxies per unit magnitude per unit megaparsec cube. And magnitude is a way of astronomers to measure the luminosity. The magnitude is the log of the luminosity of a galaxy. And so we can see here how many galaxies we have per unit magnitude or luminosity per unit volume in cubic megaparsec as a function of how bright or faint the galaxy is. So the magnitude on the horizontal axis. And we have bright galaxies, negative magnitude numbers for astronomers, and faint galaxies, less negative in this case. So greater magnitude means fainter galaxy. And here galaxies have been separated by redshift or distance. So the higher the redshift, the more distant the galaxy, and the earlier it is observed. So we can see here the luminosity functions going from redshift 10, half a billion years after the Big Bang, to redshift 4, or about 1.5 billion years after the Big Bang. And we see that there is quite a strong evolution in the numbers. We start out at early times. We have less galaxies per unit volume at fixed luminosity than at later times. So we are building up progressively the galaxy population. And this is a logarithmic scale on the vertical axis. So in just a relatively short amount of time, we're growing the population of galaxies by several orders of magnitude. Let me see, we have a question on this. So if we find a very distant galaxy and we keep observing, well, if we would get essentially the same information, because galaxies evolve on very long timescales. Over timescales of a few years, even the lifetime of an astronomer, 30 years, even 100 years, even civilization timescales, thousands of years, not much is happening in a galaxy. So we really need to study different galaxies at different times. We cannot wait to see individual galaxies changing significantly. We can do so for some stars at the end of their lives when they explode as supernovae. That's a very rapid phase of evolution. We can do that. But for galaxies, unfortunately, our timescales are so much shorter than the evolutionary timescales for galaxies, then we will not see any variation. So we have to study populations of galaxies. And here I am showing you just one result that I recently obtained from my group, just to highlight that as we go toward more and more distant galaxies, this is a redshift 9 luminosity function, about 500 million years after the Big Bang, obtained with the Hubble Space Telescope with an observational program called BORG, the brightest of reionizing galaxies. We found a couple of galaxies that are already brighter than our own galaxy. And that's quite amazing, I find it, because the universe was only 500 million years old, and yet we had galaxies probably already with 10 billions of young stars shining ultraviolet radiation, which is brighter than the one from our own galaxy, and then it's observed that the light travels to us, it's redshifted a factor of 10, and we observe it in the near infrared. So that's the current frontier. With Hubble, it's very hard to go further back in time, and we'll see what else we can do to observe even those more distant galaxies. But let's now take all those observations of the galaxy luminosity functions at different times or redshifts, And let's say, well, I now take how many galaxies there are at each cosmic epoch, and I transform the amount of light that I observe from those times to how many stars are needed to produce it. So I go from a luminosity function to a star formation rate at a given redshift. And so from those observations of these distant galaxies, we can construct what is the star formation rate or the galaxy formation history of the universe, which is shown here in this plot. On the vertical axis, we have the log of the star formation rate, solar masses per year in new stars formed per unit volume in cubic megaparsec, as a function on the horizontal axis of redshift or of age of the universe on the top. And we can see that we start out at the earliest times observed by Hubble, where we have a star formation rate of about 10 to the minus 3 solar masses per year per cubic megaparsec, which is pretty low. Then it grows quite rapidly. There is a golden age for the formation of stars and galaxies a few billion years after the Big Bang, and then the star formation rate declines in recent history. And we can infer that this behavior is related to then two elements: the assembly of dark matter halos that give us the rapid growth at early times, and then the progressively larger impact of dark energy, which is fueling an accelerated expansion of the universe that contributes at later times to bring down the star formation rate. Let me see, we have a question on the SDSS spectra. Yeah, so here I'm showing you the so-called Maddow-Lilly plot. So we observe the galaxy luminosity functions and we infer a star formation rate at those at the epoch of the luminosity function determination. And a different approach would be to observe individual galaxies, take spectra and reconstruct their star formation histories. And then so we can see how the stars of that galaxy were built at different times. And that indeed has to rely on detailed modeling and analysis of the spectra. And in general, we have then to worry about issues such as extinction, because the amount of dust that we have in a galaxy can mask the ages of the stellar populations that we have there. But the method here is a bit different. They are very complementary and they can all help us to understand how galaxies formed and evolved. And just to iterate on this point of broadband imaging versus spectroscopy, when we are looking at distant galaxies with the Hubble Space Telescope, we can get only a very limited range of intrinsic wavelengths. So because of this very significant redshifting of the photons, we observe with Hubble only rest frame ultraviolet photons. And from those, we cannot get a full picture of what those galaxies look like. We need rest frame optical observations that in order to, for example, understand what are the ages of the stars in those galaxies, because we can have young stellar populations having fairly flat spectra across wavelengths. We can also have older stellar population showing greater 4,000 Armstrong Balmer breaks. So the RS frame optical is brighter than the RS frame ultraviolet for older stellar populations. Also, because those distant galaxies are generally photometric candidates, it's important to have further observations, such as ones that were obtained until last year with the Spitzer Space Telescope, which was an infrared telescope now unfortunately no longer operational, could also help us distinguish between those faint red sources that are true galaxies in the youth of the universe at high redshift versus galaxies that are masquerading as such, which we call interlopers. Galaxies at lower redshifts that have a lot of extinction, a lot of dust, for example, such as the track shown here on the top. And so the details can be quite challenging to figure out, but astronomers have been very good at this game of building reliable samples of high redshift galaxies with broadband images. So once we find them, then we can also do follow-up observations with other telescopes. And here we go back to the question that we addressed earlier of it's expensive to put big telescopes on spacecrafts. So we find the distant galaxies with the Hubble Space Telescope, and then we can try to follow them up to take spectra with the very large telescope from the European Southern Observatories, with the Keck telescopes, Mauna Kea. We can do also millimeter wavelength interferometry follow-up with the ALMA interferometer. So with these studies, we can try to detect Lyman alpha from those sources. We can study the neutral fraction of gas, of hydrogen gas in the intergalactic medium. We can study in particular with the ALMA observations, the stellar populations in greater details. So, okay, so there is a question on gravitational lensing. Yes, when light passes close to a significant mass, it gets bended, it gets redshifted as a result of the being in a strong gravitational field. But the light, the net effect is not a significant change in frequency, because the light enters the gravitational field and then exits it. So essentially those two effects cancels out. So the gravitational lenses are very useful to concentrate the light and help us get even more magnified view of distant galaxies, but we don't have to worry too much about the change in redshift. So let me spend now the last maybe 10 minutes or so on a bit of the theoretical interpretation of those observations that we have with the Hubble Space Telescope. So why does the galaxy luminosity function evolve with time? What are the main drivers of the formation and the growth of galaxies? Well, to frame the observations that we do with the Hubble Space Telescope and with other telescopes on the ground and in space, we can think that galaxies form within dark matter halos. So the working hypothesis that we will make is that the evolution of the dark matter halo abundance is the main driver of star formation at early times. This is justified because we know that there are two main modes to grow a galaxy. We can have a steady accretion of primarily cold gas being funneled by filaments into the galaxy and fueling new star formation, or we can have merger-triggered star formation. When two galaxies crash into each other, there are shocks, the gas undergoes the right physical conditions for then cooling and forming new stars. And both these processes are driven by gravity, and therefore, since there is about 5 times more dark matter than baryonic matter, dark matter is the driver of all these processes. And if we look in cosmological simulations at how the structure, the dark matter halo structure assembles at early times, we can see that the galaxy forming regions have over densities of dark matter halos compared to the average regions. So we can think, well, as we go toward higher and higher redshift, the universe becomes more and more homogeneous. So halos at a fixed mass become rarer. So we can indeed expect that evolution in the luminosity function. Fewer galaxies of given mass or luminosity as we go to earlier times. Quantitatively, we can model this link between dark matter halo mass function and the galaxy luminosity function. We can take one, say, well, I place one galaxy in every dark matter halo, and the star formation efficiency in that galaxy will depend on the mass of the dark matter halo. If we do so, and myself and the collaborators have done it in a few different flavors of modeling, we get some pretty good description of the evolution of the luminosity functions. So in this figure here, I'm showing again luminosity functions, so number of sources per unit luminosity brightness per unit volume as a function of brightness of the galaxies in absolute magnitude. So again, we have bright sources on the right and faint sources, bright sources on the left and faint sources on the right. And we can see that the model predicts quite nicely the decrease in the galaxies going from redshift 4 on the top in yellow to where the observations are at their limit in red at redshift 10. And we can see this characteristic function, which is called the Schechter function, which is a power law at the faint end on the right, and an exponential drop-off on the left for the bright galaxies. And the black holes, indeed, they are crucial in regulating star formation. So the lack of very bright galaxies, for example, is associated to the feedback that the energy emitted by the accreting black holes is injecting into the galaxy, preventing further star formation. So the so-called AGN feedback, active galactic nuclei accreting black hole feedback, is what is contributing to giving this shape to the galaxy luminosity function. We see it's quite well described by the model by Schechter shapes, but we have at the moment reached a relatively limited understanding. We can count sources quite well, but they are fuzzy blobs. So we don't really know at this stage yet if the luminosity function remains of this Schechter-like shape at the very high redshift, how efficient is star formation in high mass halos, or equivalently, how efficient is the supermassive black hole feedback in those high mass halos at early times. And the galaxies such as GN Z11 that we see here, are those very young galaxies, or do they have relatively old stellar populations, so maybe a couple 100 million years old? What is their environment? How many metals, the heavier chemical elements there are? Is there dust which is introducing reddening? So to make progress on these topics, we are all, as astronomers, keenly waiting for the next generation very powerful space telescope called the James Webb Space Telescope, which will hopefully be operational in 2022. And James Webb will be able to observe galaxies in the first 400 million years, which are still mysterious to our observational views because these galaxies are too distant. Their light gets shifted too much into the red. They go out of the observing window of Hubble. In contrast, James Webb has been designed to observe in the infrared out to 28 micron, has a larger mirror, 6.5 meter in diameter. So it will really allow us to see the first generation of galaxies, possibly the very first galaxies that formed maybe 300 million years after the Big Bang. This is a simulation on the bottom showing how the James Webb will improve over Hubble images, giving us more details and a view further into the red. To iterate this point, I have here another simulation that I've done with one researcher in my group recently. That's a simulated bright Milky Way-like galaxy at redshift 7, or about 750 million years after the Big Bang. In the rest frame ultraviolet on the top, this is how it is observed with Hubble on the top left. Spitzer Space Telescope, which was giving us a rest frame optical until it was decommissioned last year, was only a small telescope, 80 centimeters in diameter. So was giving us essentially no resolution on this galaxy. In contrast to the James Webb, you can see how it will be able to resolve with much greater detail and give us the rest frame optical view of this simulated galaxy very, very effectively. Most of what I've presented today was focused on star-forming UV bright galaxies. Another very interesting aspect of star formation is how do the passive galaxies, the quiescent elliptical galaxies form, and when do we find the first elliptical galaxies that generally have older stellar populations. Colleagues such as Professor Glazebrook here in Australia at Swinburne University of Technology are making some really interesting observations with the Hubble Space Telescope and with ground-based telescopes, and they're finding elliptical galaxies already at relatively early times, redshift greater than 3. So one key question that the James Webb Space Telescope will allow us to address is how early do these systems form? Can we find elliptical galaxies all the way in the first billion years after the Big Bang, and how early were the first elliptical galaxies formed? So this brings me to the end, toward the end of my talk. I will just mention very briefly that if you're interested in some of the Hubble images that I've shown, in general, a really good resource for amazing images from stars, galaxies, and black hole, and accreting matter that Hubble has taken, exploding supernovae. If you are maybe a science teacher in high school, if you give a presentation for the public, go on hubblesite.org. It is a really wonderful source of information with explanations also on the science behind those amazing pictures obtained with Hubble. If you're interested in doing some research projects using Hubble Space Telescope data, the Hubble Space Telescope project has the policy of making all data public within at most 1 year after they are taken. and the data are organized in a really friendly archive. Some data have already been processed and are even ready to do additional science investigations. So the Hubble Legacy Archive is a great resource for this. Of course, you need some guidance and training if you wish to use astronomical images for research and you had not had an opportunity to do so in your university education yet. So I will just conclude by advertising the Kathmandu Astrophysics School, which myself and collaborators have started back in 2016 to improve the opportunities for young researchers in Nepal to access additional educational opportunities and opportunities also to network with committed peers and with mentors coming from multiple countries abroad. So we had 2 editions of the Kathmandu Astrophysics School, one in 2016 on order of magnitude astrophysics, one in 2018 as an introduction to computational methods in astrophysics. And now we received the funding from the International Astronomical Union Office of Astronomy for Development to do a 3rd edition of the school, which will be focused on introduction to observational astrophysics. So you will have the opportunity to learn some of the techniques to analyze data, for example, from the Hubble Space Telescope, if you're a participant of the school. We were initially planning to have it at the end of 2020, probably due to the COVID-19 pandemic. The dates will be shifted a little bit, and we're looking at having a mix of remote learning and the first part to start engaging with the selected participants, and then in-person school, likely in Pokhara, like in 2018, once it is safe to travel again. And that might happen then the second part in 2021. Details are coming soon. We're preparing a website. We're preparing applications forms, which will be widely advertised. And I expect that applications will open sometime in July and remain open throughout August. And I encourage you to consider applying for the school or advertising the school to other students who might be interested in taking advantage of this opportunity. So I think I'm now very happy to take questions. In doing so, I will just start addressing some of the questions that the organizers of the talk and of the seminar have been sending me via email that some of you have submitted early. So the first question was, what are the computational approaches being taken for modeling of formation of cosmic level structures in the early universe? Well, I hinted a little bit in my talk. Generally, astronomers are using the so-called cosmological magneto-hydrodynamical simulations that simulate in a computational volume with billions of computational elements the evolution of dark matter, density fields, and of the gas, the baryons inside, with subgrid recipes to form stars. And so we can form the first generation of stars, we can form galaxies, and then compare the results from the simulations to the observations that we have with the Hubble Space Telescope, for example. A related question is, what could have been the role of dark matter and dark energy in the formation of galaxies after the Big Bang? And I think I've already hinted at the answer when I was presenting the star formation history of the universe as a function of time. So dark matter drives the gravitational collapse of halos inside which galaxies form. And so the dark matter also determines the cosmic web, how galaxies are distributed in the universe. So essentially, dark matter tells galaxies where to form and where to be. Dark energy instead, which is fueling an accelerated expansion of the universe, is pushing galaxies and the dark matter halos further and further apart from each other, is making the collapse of new structure harder. So it's suppressing galaxy formation. And that started a few billion years ago, and it's becoming more and more prominent as time will pass. The question on cosmic rays then. Are there any unusual phenomena seen in cosmic rays during the formation of galaxies? Well, cosmic rays are really an active research area at the moment. They likely play a very important role in driving the galactic outflows when we have exploding supernovae in star-forming regions, and that, especially in the smallest galaxies, regulates star formation. The physics of all this is very, very difficult to model because there is an extreme dynamic range involved. You need to model the formation of cosmic rays at the level of shock waves in supernovae and then resolve sufficiently large areas to have multiple galaxies, or maybe even just one galaxy. That's a growing area of numerical astrophysics, something which the modern complex cosmological simulations of galaxy formation are looking into it. Related question is, what is the effect or influence of the magnetic field in the formation of the universe? And again, magnetic fields play a really important role in star formation. They definitely contribute to creating turbulence in the interstellar medium, which in turn affects how stars are born out of the gas. Magnetic fields, connecting to the previous question on cosmic rays, also impact the production of cosmic rays and then galaxy evolution. It's really, really very hard to model magnetic fields. So if you have something unexplained, sometimes astronomers tend to say, well, maybe it's because we don't consider magnetic fields, so it will be magnetic fields which explains what we don't understand yet. But progress is being made, both with simulations and also with some observations. This is a recent observation of the magnetic field in a nearby spiral galaxy, obtained with radio observations for using polarimetry. And the magnetic field is shown to be connected to the spiral arms of galaxies. So that's really interesting and an active area of research. So I'll finish here with the summary, and then I'm very happy to take more questions. So what I've told you today is that we can observe the galaxies in the young universe in the first billion years with the Hubble Space Telescope, and Hubble has really transformed our view. We can count the galaxies well with Hubble. We understand, we have seen why the luminosity function evolves in the way that we observe, but still we don't know the details of these galaxies that we observe. They are still clouded in quite a bit of mysteries. But the future of the field is bright. There is progress both expected with future observational facilities such as the James Webb Space Telescope, or with complex numerical simulations, and of course with theoretical modeling as well. So there are plenty of opportunities for new generations of researchers such as yourself to contribute. So let me now look at some of the final questions that we got so far. Resources, well, links, I can share a PDF of this presentation. I also understand that this presentation is being recorded, so you will be able to watch back the slides if you contact the organizers. Online courses on astrophysics, I think Coursera has a few good astrophysics courses, some on, for example, radio data techniques or high energy X-ray observations from Space Telescope. So there are a few good resources out, and the number of high quality online education is growing at the moment. So let me see this question on elliptical galaxies. So generally, so elliptical galaxies are quite interesting. So the elliptical galaxies have mostly older star compared to spiral galaxies, less gas, and we think that it's primarily because elliptical galaxies form out of the collision of spiral galaxies. So you start with spiral galaxies when you form the first generation of stars. Then you have galaxy collisions, and so you tend to rearrange all the orbits of the existing stars. So you tend to consume all the gas that is in those galaxies. So you're left with a puffed up version of a spiral galaxy without the disk. You then form an elliptical galaxy. And so understanding how early those elliptical galaxies can be observed is quite interesting to constrain the ways in which these objects can form. For the expansion of universe, what will give the space? So that's a really good question. So it's not that galaxies are moving away from each other inside the space, but it's the space itself which is growing. Here we would go towards cosmology, theoretical physics to understand what is happening. We think as a way of representing it that the space, our three-dimensional space we are used to, is expanding into a fourth dimension. So is a space itself which is growing in our concordance cosmological model. There is one question on the expansion of the universe and the speed of light. Well, the speed of light is finite and applies only to information, to photons moving inside the space. The expansion of the universe itself can happen nominally at any speed, even larger than the speed of light. When we look at these very distant galaxies, these redshift greater than 1 sources, formally, if we look at the low velocity expansion, they would have apparent velocities with respect to us that exceed the speed of light. And that's not violating any physical law, because indeed the cosmological redshift is given by the expansion of space itself, is not given by the relative motion of objects in regards to each other. So it's very different from the Doppler shift. So on Hubble constant, so the Hubble constant There are different, that's a really interesting area of astrophysics, precision measurement of the Hubble constant. We're pretty confident it's about 70 kilometers per second per megaparsec, but exactly is it 67.4 or is it 72 is a really good problem to work on to understand better the evolution of the universe. And at the moment, there is a bit of tension between the value of the Hubble constant that we measure if we measure it from observations such as the cosmic microwave background from the Planck satellite, for example, versus if we observe it from the expansion of the universe locally, using nearby galaxies, Cepheids, and supernovae. And so this discrepancy between the Hubble constant that inferred from early times measurements and late times measurements might indicate that maybe our cosmological model is not quite as complete as we think it is. Then I have a question on how to generate a PSF of the sources. I can share some information through the seminar organizers. In general, you can do very simply a convolution with a Gaussian kernel for a PSF. It's not a problem. If you go on the Hubble Space Telescope archive, you can even find PSF for the Hubble Space Telescopes derived with very sophisticated modeling. So it all depends on the problem that you're trying to solve. My advice is never try to complicate your analysis more than you can. If you can approximate the PSF with a Gaussian kernel, you should do it. You can then make it very simply in Python, in MATLAB, Mathematica, whatever source you're using to create, to manipulate your data. So there are always new theories on galaxy formation, evolution, on cosmology itself. It's a very active area. I think we have a broad understanding of what's going on, but many details and maybe some surprises are waiting for us to be clarified. In particular, keep in mind that the universe we see, we can study directly the baryons. It's only 5% or so of the total energy density in the universe. The remaining 25% or so is dark matter, and we don't have yet direct observations of the particles constituting dark matter. Further, the dark energy, 70% of the universe, is quite a big mystery. We have no idea about what it is, besides what it is doing to the expansion of the universe. So I would stay tuned for some surprises. What are the factors important for shaping galaxies? I think, well, the angular momentum of the gas out of which galaxies are forming is the most important factor to determine whether you have a spiral galaxy or whether you have something which is closer to an elliptical galaxy. Another factor is whether you have collisions between galaxies, initial conditions that give you collisions. They shape galaxies quite differently. You tend to have, at least for a while, irregular galaxies, interacting galaxies. The amount of radiation that you have around the galaxy, that will impact how many stars you can form. The chemical composition of the gas, again, will impact the properties of the stars that you form. So a very good question on Andromeda Galaxy. So we know that the universe is expanding and everything is going far away from us, but Andromeda Galaxy is closing to the Milky Way. Why is this happening? Because Andromeda and the Milky Way are gravitationally bound to each other. So the space between Andromeda and the Milky Way no longer expands. So gravity has taken over. So indeed, Andromeda will collide with our galaxy in maybe 1.5 billion years or so. And at the same time, the universe on a very large scale will continue expanding. Yeah. And yeah, I think I have a question on the lifetime on the photon. I think that based on our current understanding, the photon is a stable particle, so it can survive for the whole age of the universe. And indeed, with the cosmic microwave background, we are observing photons that were emitted at much higher frequencies, shorter wavelengths, just about 300,000 years after the Big Bang, when radiation decoupled from matter, and we are observing today as 2.7 Kelvin black body radiation. What is the main reason for the expansion of the universe? Well, we don't know. I think that's the short answer. We had the Big Bang, which imprinted initial conditions, a very rapid expansion. Gravity slowed down the expansion for a while. Dark energy, now it is accelerating it, and we have no idea about why is that happening. Yeah. So how did the first galaxies in the universe form, and how did they make the universe transparent to light? So that's a really good question. The first galaxies, we think that they formed in sites where we had formed a few first stars. So we form first stars first out of gas that has only hydrogen and helium. So we call them metal-free stars. They are very massive, maybe 100 solar masses as characteristic mass. They produce heavier chemical elements, they enrich the gas, then the gas mixes, there is a more massive dark matter halo that is collapsing with the gas inside it and can form a first galaxy. Then the first galaxies, they have a significant emission, young stars, UV radiation, so they ionize the neutral hydrogen. So that is why we say that we are the first galaxies live in the first billion years as the epoch of reionization. And so that is making also the universe transparent to those high energy radiation. Otherwise, high energy photons in the ultraviolet only travel very short distances before being absorbed by neutral hydrogen gas. So before first stars, that's very difficult to observe. So we can do observations at radio wavelengths, observing the redshifted 21 centimeter emission and absorption lights, and that is I think the most promising approach to go before the first stars. Of course, the cosmic microwave background is the best tool that we have to understand how the universe was when very, very young, just as I said, about 300,000 years, 300,000 years after the Big Bang, at a redshift of about 1,100. What is the local group? The local group is a group of galaxies comprised of the Milky Way, the Andromeda Galaxy, another dozen or so of medium-sized galaxies, and then maybe 100 small galaxies, dwarf galaxies, that is all gravitationally bound to each other. And we call, so it's a group of galaxies. They are fairly common in the universe. Galaxies live in groups. These small villages of galaxies, order of 100 galaxies per group, or in small towns, the galaxy clusters that can have thousands of galaxies. Isolated galaxies are relatively rare, and we call it a local group because it's local here to where we are in the universe. So how did the stars that are more massive than about 10 times the mass of our sun, they explode as type 2 supernovae at the end of their lives. So they release very effectively the chemical elements that they transformed through nuclear fusion in their cores. Also, these supernova explosions produce the heavier elements beyond iron. So we produce the chemical elements, we have kinetic and thermal energy from the supernova explosion that can create galactic winds and galactic fountains. So this chemically enriched gas gets then mixed with the pristine gas and can start forming subsequent generation of stars and new galaxies. And sometimes these outflows are so powerful that they even escape the gravitational field of one galaxy and they can reach nearby galaxies. And I have a few questions on parallel universes and like what is time, what is the universe itself. Those are questions that I really cannot answer. They are both outside my area of expertise. Also, they start becoming quite challenging to address with the scientific method, which is based on formulating theories, hypotheses that are falsifiable. And it's something which tends to move a little bit more towards philosophy. But there are many interesting theories about the bubble universes, parallel universes. You might look into experts in those areas for answers. So if there are no further questions, I think we've run a little bit over time. So I suggest that maybe we bring the webinar to a close, and I thank you all very much for all these really engaging questions. It has been a pleasure to present to you today, and I'm hoping that I'll be able to meet some of you at the next edition of the Kathmandu Astrophysics School, when we will be able to come to your beautiful country and to the foothills of the Himalaya in Pokhara, hopefully in 2021. Thank you all.